This talk is basically all about the topological insulator and its quantum transport properties. This talk has been carried under the outlines: first, what is topology; second, what is topological insulator and its physical connection; how topological insulator works; role of Kramer's degeneracy in topological insulator; spin-orbit coupling; time reversal symmetry; wave function; quantum transport properties like weak localization, weak anti-localization, and quantum oscillations, and quantum conductance properties like conductance quantization. What is topology? Topology is basically a mathematical term which basically deals with the systems under some invariant conditions, but externally there is no twisting and tearing, bending, tearing during the deformation process. Like this donut has been shown here, there is continuous deformation in coffee mug and donut, but there is no tearing and externally bending, stretching, twisting. This showing the continuous deformation in coffee mug and donut. So this is protected under the genus. Like here genus is equal to 1 in also the donut and coffee mug, and similar to that the under Gauss-Bonnet theorem, this is also topologically protected due to their surface area is topologically protected. And this is the second example which states that the sphere there is no genus, and to calculate by the Gauss invariant theorem and surface area calculation by integral method, this states that the surface area is equal to 4 pi. Because there is no genus here, this is equal to 0, so the Gauss invariant theorem is also invariant in the sphere. So this is the Gauss invariant theorem which basically deals with the systems. There are two examples, coffee mug and genus, which are in the same class because they are the only the one genus here, and the calculated area of under the Gauss-Bonnet theorem, this is equal to same. And other examples are like these are the three examples in which there is no genus. So there is no genus and the calculated area under the Gauss-Bonnet theorem surface area calculation, this is equal to 4 pi. So these three are in the same homomorphic class and these are two in the same homomorphic class. So as long as the genus is protected here, so long as the topology is preserved here. So this like in the case of the sphere, if we externally pressure this sphere like we consider as a football and like a balloon, and if we externally pressure this more and more and the balloon disturbs and it breaks, so the topology is protected. But if the balloon change their shape like sphere to ellipse and some other shapes, but there is no hole, so so by that the time this protected the topological nature. In physics, basically in condensed matter physics, the topology deals with the topological insulators and topological crystalline insulators and many other materials like wise semimetals, dark semimetals, in which the topology is protected, and the protected topological are of the various symmetries. Like in topological insulator, the topology is protected by the time reversal symmetry, and in topological crystalline insulator it is protected by the crystal symmetries. Mainly it is protected by the mirror symmetry, and many times it is protected by the inversion symmetry. And some other examples also like wild semimetals and others, all they are also chiral behavior, they are also protected by the spin chirality of the wild semi nodes. So this states that the protected topological under coffee mug and donut, which are they are the topology protected. And why they are topological protected? Because in coffee mug and donut there is only the one genus, and if we deform, like if we consider like a donut is of, it is made of the rubber. So if we stretch this donut, we can change many shapes. But under the deformation process, if the genus is protected like equal to 1, so this is also protected in the topological nature, because every time there is only the one genus and the surface area under the Gauss-Bonnet theorem, it also remains same. So in we consider the coffee mug and donut, because in coffee mug there is also the one genus and donut also the one genus, and both surface area is equal to same, so which have the topological protected. So with the consideration of the these mathematical equations and terms with the physics, in physics this it is means to be that the properties are protected under the symmetry protection. They are protected the band inversion symmetry, like the bands are closing without closing the energy gap, and the property it is protected uh, by their symmetry in the bands, means to say that the energy bands of the materials are considered like the billion zone. Basically 2D billion zone is considered like a donut. So the electronic properties are preserved if we not externally perturb the systems, and they are protected under symmetry. We are discussing one by one. So this is the case of the deformation of the billion zone. So PVT, the lead telluride, which is basically not a topological insulator. So here are the properties like that. There is no in the band conversion here, valence band to conduction band. There is no any interchange to each other. But here the NSNT, which is a topological material, showing the conversion. It means to exchange of the bands like valence band to conduction band and conduction band to valence band at the high symmetry points. So similar to the deformation process of the billion zone is equivalent to the band diagram of the conduction band to valence band. In the high symmetry points, the symmetry points states that if the interchange of the bands valence band to conduction band, they are at the high symmetry points similar to that of the valence band to the conduction band in the deformation of the billion zone. And it is basically stated that if we deform the billion zone by several ways, but if it is not if it is preserved by that symmetry, like if the system is protected by time reversal symmetry, so it is must required to it contain the time reversal symmetry as long as the system to be preserved in the topological material. Like other symmetries like translation symmetry, rotational symmetry, mirror symmetry, if the system are protected in the crystal symmetries like translation symmetry, so it is required to be that up to the topological period in the system, translation symmetry remain to be invariant. So during that time the bands are also remain finite and overall band structure is preserved. We are showing in the again. So the roles of the Kremer's degeneracy in the materials. So this Kremer's degeneracy is basically related to the spin orbit coupling materials and time reversal symmetry. So because of that, at the Kremer's pairs, the spins are in the helical ways, and in these spins are in such a way that if on at the one edge state is spin in the up direction and it is moving right, then on the another edge state the spin is down and it is moving on the different direction. So as long as this system is preserved, and means to say that if spin change the direction, so on the other edge is spin also change the direction and their momentum. So this is states to be that the time reversal symmetry holds here, and up to that the time reversal symmetry hold in the system, the system to be in the topological nature. And up to the operation of the symmetry, like it may be the time reversal symmetry and it may be the crystal symmetry, the overall Hamiltonian are preserved up to the time individual symmetry, and it commutes with the system. So as long as the Hamiltonian commutes with the symmetry option, so long as the topology is preserved in the system. And one important thing is that these helical edge states means to say that these are the edge states, like they are in the Kramer's degeneracy, means to say that electron can either reside either the yellow state and the blue state, but at the same time it can reside only the one, because it explores the Pauli exclusion principle. So similar to on the other edge states, electron can either reside yellow and blue. It can maybe either the blue and yellow. There's the choice of the electron, but at one time it can decide only the one edge state. More clearly, we have shown here in the like states, these states like N1 states, these are in the Kramer degeneracy, and these are also in the Kramer's degeneracy, and this is the stretching of the photohole under continuous deformation. But if we are seeing there here that under the stretching the photohole change their shape into the ellipse, but during this deformation this protected their genus, and overall surface area under Gauss-Bonnet theorem is 4 pi. So this is the topological protected. And in the band diagram of the topological materials, they are the continuous in the deformation process, either balance band to conduction band, as we have tell in the previous slides. Like this, the band diagram are in the continuous deformation across the symmetry points. So this to that, basically these bands are in the Kramer degeneracy forms, and with this that means to say that how the topology is preserved in the topological system, because these edge states are in the Kramer degeneracy. With this that the electron can either reside yellow one and blue one, but at a certain time it can reside in the particular in only the one edge states, and as the electron change the direction of their spin, also change the direction of their momentum. So as long as this condition holds, so long as the topology is preserved. One important thing is also that if electron is in this state below, yellow can also be in the below, because they are in the Kramer degeneracy. But the spins are also, it is required to be opposite and momentum. So this is basically the wave function of the electrons of the topological materials, and there are the total possibilities of the wave functions are number in the 16. So how the topological material and trivial materials interchange to each other. So this is the band diagram have been shown here. This is the trivial insulator. There is the large gap, electron cannot go from valence band to conduction band, so there is no conductivity. But at this deformation, at a certain value of the edge, at a drag point, there is the drag semi-metal, and there is the conductivity only as a single point. But in the topological materials, there are the spins, opposite spins on the edge states, and they are in the continuous deformation. Electron can move along the S like this. Means to see this, electron can move like this on the edge states and this edge states. So there is a continuous deformation. This is the topological balance band to conduction band, continuously change, but there is no possibility to like in the drag semi-metal. And this is the case of the topology to trivial insulator to non-trivial topological insulator. There is the continuous deformation of the band diagram. Electrons interchange to each other like to this way. So the quantum properties of the topological materials, these are some specific properties are discussed here. The weak antilocalization and weak localization in the topological materials, quantum oscillations, conductance quantizations. So one by one the property has been discussed here. This is the weak localization and weak antilocalization in quantum transport in topological insulators. First here to be discussed is that what is weak localization and weak antilocalization in resistivity and magnetoresistance. What are the causes of arising weak localization and weak antilocalization? Classical and quantum probabilities of these phenomena means to say that the weak localization how to appear by the classical probability and the quantum probability similar to in the weak antilocalization. Role of interferences, either destructive interference and constructive interference. Effect of magnetic field, how magnetic field perturbs the properties and to break the weak localization and antilocalization. Effect of phase factor on conductivity, which change by the magnetic field, and it may be by other several properties and several disturbances. So this showing the conductance of the magnetic field. As the magnetic field is increasing, the weak antilocalization suppressing, and at a certain value of the magnetic field, this is completely suppressive here, and this showing the conductance has been flat up to a certain value of the magnetic field. Generally in uh, very ideal systems, it comes across very low domain of the magnetic field, which is generally minus 0.5 Tesla to plus 0.5 Tesla. So what is weak localization in resistivity and magnetoresistance? So this is the basically very rapid change in the resistivity of the material. Generally it is due to perturbed by the magnetic field, and it is the magnetoresistivity, and it occurs in the very low domain of the magnetic field. This is the typically range of the weak localization and weak antilocalization in the ideal systems. And magnetoresistance decrease with the increment of magnetic field, shows negative magnetoresistance. So this is the weak localization. And weak antilocalization, it is the positive magnetoresistance. With the magnetic field the resistance increases, and it occurs in the very clean systems, like with the spin orbit coupling, which has the particular materials, gives very good weak antilocalization signatures. So they are basically occurs also in the like to me to say that in the drug materials and also the superconductors, but these are also basically good occurs and good phenomena of the spin orbit coupling materials. So these are the signatures, this showing the positive magnetoresistance, and this is the cause of arising in the weak localization and weak antilocalization. So weak antilocalization also observed in the clean systems, but weak localizations are come in the disordered systems, like electron can undergo multiple elastic scatterings, and it may be that the system also in the note in the case of the ordered systems, like means to say that during the growth of the system has several defects and disorders, due to which also weak localization occurs. But to be occurs of the weak antilocalization, the system is required to be the robust spin orbit coupling systems, and it reduces the back scatterings and coherent back scattering of electrons, uh, due to which that in the disordered conductors. So these effects are also observed. But in the topological materials, because the topological materials are also the high robust spin orbit coupling materials, which reduces the back scattering and gives the weak antilocalization signatures. But by perturbing the systems and to break the time residual symmetry and to disturb the spin orbit coupling, like to many external factors, but generally as the papers state that they are trying to break the time residual symmetry by the magnetic doping, and after the doping that there is the gap open across the surface states, uh, due to which this showing the weak localization signatures. So on the basis of the classical probability, so we cannot explain this phenomena, because the electron is also the quantum particle, and in purely classical system electron motion is in the disordered case, and this shows the diffusive transformation, and it reduces to the electron to be returning their probability, and means to say that the electron scattering is the randomized, because means to say that electron here it is the probability of the electrons to be scattered randomized, means to say that electrons are not in the ballistic case, means they are into the diffusive case. Electron cannot relax to further to again quantum coherence with the electrons, means to say that the relaxation time is very less in the case of the classical probabilities. But in the case of the quantum materials, the electrons are in the ballistic conductance properties, means to say that the electron interaction in such a way that the electron can relax easily to before again to go into the conduction state, due to which the mobility of these electrons are very high, because the band formation in these materials like the very high dispersive bands are either in the case of the flat bands kind of the materials, due to which on the edge states the electron can the probability and the band behaves like the drag peaks, and on the flat band because electron cannot travel here because there is no curvature, and on the flat band because of there is no curvature, so the electron cannot go here, so there is no going to the conductivity. But on the edge states electron can rapidly move, because this showing the drag peak kind of the behavior, and also showing basically the dispersion bands. In the dispersion bands also there is the linear dispersion band, highly dispersive band in which basically the electron mobility is very high. In compared to the classical bands like the parabolic bands, because there is the curvature is there, parabolic curvature is there, so the probability of the electron to move is very less. So in the parabolic bands the electron mobility is very less. But in the topological materials these are the different because of the dispersive and flat. So in the by the classical probability we cannot discuss this. By the quantum probability we can discuss the motion of the electrons, and because of the coherence of the means to say that the constructive and destructive interference of the electrons, uh, because in the returning probability is very high and hence leading to higher resistivity at low temperatures in the case of the weak localization. Because there is the constructive interference we will discuss again in the further slides with the various animations. And weak antilocalization cave, this is the spin orbit coupling materials, and between the spins this shows the pi phase shifts, and due to which by that time vessel pass and destructive interference and reduce the back scatterings and lowering the resistivity. We will discuss this weak antilocalization also by several animations. And in the case of the topological insulator, so the important criteria how the weak antilocalization and weak localization occurs in the materials. So this it is required to be that the particle size should be greater than that of the coherence length of the electron. If between two electrons the coherence length is lesser than the particle size, so electron cannot coherent to each other, means to say that they not interact with each other, so reduces the probability of the weak localization and weak antilocalization in the topological materials. Means to say that if the coherence length is less than that the particle size, so in a single particle the electron cannot interact to each other, means to say that they cannot either the constructive and destructive interference, so there is the reduce the probability, either they cannot go into the weak localization and weak antilocalization signatures. So again to be that this coherence length should be greater than that of the electron mean free path, because this is also required to maintain the phase coherence of the electrons. If two electrons cannot interact to each other, they cannot go into the several quantum interferences effects, and they cannot go into the conditions like weak localization and weak antilocalization signatures. So this important is that then only quantum interference between time universal scattering lobes like this. If electrons cannot interference to each other, they will not go the quantum interference. So on the basis of the classical probability, we cannot explain this because of the classical probability. So there is a very high probability of the electron to find at a certain position. So electron reside only a certain position, it cannot here and there. So with this that we cannot explain this probability of the scatterings like weak localization and weak anti-localization signatures. But on the basis of the quantum mechanics, we can clearly explain the weak localization and weak anti-localization signatures of the topological insulators. And here we consider the two electrons. One is of the clockwise electron, with this the phase of the electron. This is the counterclockwise electron, the phase factor of this and the corresponding wave function, and the total wave function with the clockwise and counterclockwise of the electrons. This is the total wave function. So there are the two possibilities here. If the electrons are in the constructive interference, means to say that the spin are in the parallel case, there is no angle, means to say that the angle between the spins is equal to 0. So if we put here, so this is the probability like this. So this is the very high probability of the electron to reside at a certain position. So if the electron is at a certain position, if it is not go here and there, so there is, it will not give the conductivity to be very high. Second, the destructive interference, means to say that the electrons are in the opposite phases, means to say that they are the anti-parallel. So the probability is very less. So if the electron probability is very less, so electron can rapidly go here and there, due to which this showing the very high conductivity. And in the case of the topological materials, these signatures obtain like weak anti-localization signatures in the conductivity, very high conductivity, and it is perturbed by the magnetic field we are discussing here with this phase factor. But one important thing is that in the case of the weak localization, the electron showing like the standing wave at a certain region, means to say that the electron are fixed at a certain region. This is localized. It cannot go here and there, due to which the conductivity suppresses. But with the magnetic field, and we are discussing with the weak anti-localization signatures and to be studied here, means to say that if with the magnetic field there is the externally phase factor, because the magnetic field rotates the direction of the electrons, and due to which the phase coherence is disturbed between the electrons, means to say that if two electrons are not in the destructive interference, because these spins are perturbed by the magnetic field and they are rotates in the direction of the magnetic field, so the phase is no longer constant here. With this that the probability is disturbed, and with the magnetic field the electron probability to be localization is increased by the magnetic field, because magnetic field shows the path of the electron. It rotates in their direction, due to which the conductivity is suppresses like this way. Brief explanation by the magnetic field we have discussed in the previous slides, and we are again giving a overview. With the weak localization signatures, probability is very high, so the conductivity reduces. With the weak anti-localization signatures, opposite spins, anti-parallel, electron can go and here and there, because the probability is very less to reside at a certain position, so electron will not bound, it can rapidly move here and there, due to which conductivity is very high. But with the magnetic field, the probability is again suppresses, because magnetic field rotates the direction of the electrons in their direction and also tries to localize and disturb the phase coherence between the opposite electrons. So that's why electron cannot phase maintain their phase. That's why the probability increases, and the increasing of the probability disturbs the conductivity, means to say that the conductivity is suppresses, because probability is not again to be 0. And these are showing some animations of the weak localization. In the case of the electrons are in the same phase, means to say that they are in the parallel phase. And with this that they are showing in the case of the topological insulator, because they are in the Kramer's-degeneracy form. So these are the two possibilities showing here, electron in the yellow and blue state, and in that one this also showing the electron can in the yellow and yellow state, means to say that electron can either by this we are discussing here, electron can either reside yellow and blue, but it is in the spin up, either in the spin down. And similar to that, electron can either yellow and blue but in the up spin. And if we are considering here, if both spins are in the opposite, means to say that if both spins are in the down phase, so it is required to be that the both spins are also in down. With this that the spins are again in the same phase, there is no angle between the spins, the angle again 0. If the spins are in the down, means to say that this is the up spin, and if we rotate the direction of the spins, so but it is required to be that in this edge state and this edge state, spins are also in the same phase. This is the case of the weak localization signatures. And also again showing here, electron can either reside in this and this, but at a certain time it can also be in the one edge states. And this showing the animation of the weak localization with the magnetic field, the conductivity behavior like this. Weak anti-localization signatures with the magnetic field, increasing of the magnetic field, the resistance, the conductivity suppresses, means to say that the resistance is increases and it saturates after a certain value of the magnetic field. Because this occurs in the case of the topological materials in a very low domain of the magnetic field, and it is typically observed in the very ideal systems, approx to be minus 0.5 to plus 0.5 Tesla. And this is the animation which has been shown here. The spins are in the opposite phases, and electron can either reside in the yellow and blue, but at a certain time it can reside only in the one edge state. And similar to that, and also because of that, if electron it violates the Pauli exclusion principle holds, means to say that these edge states are in the degeneracy and the energy is same. This follows the Kramer degeneracy rule, and the electrons obeys Pauli exclusion principle. It can reside only the one edge states, but it is required to be the weak anti-localization signatures. The electron spins are in to be the opposite phases, means to say that the both the spins are up and down on the different edge states. They hold the spin orbit coupling. So these are the weak localization signatures, anti-localization at different temperatures. With the increasing of the temperature, the surface states are reducing, because at the higher temperatures the bulk are also introduces. Means to say that at very low temperatures there is no role of the bulk. Conduction means to say that there is the valence band and conduction bands are not in the participated, only the surface bands are in the participation, and due to which that the conductivity occurs. But as we increase the temperature continuously, the bulk bands are also in the participation, due to which the surface states are also suppresses. And again it's to be that, needs to say that on the higher temperatures the phonon contributions are also included here. With this that the surface states are suppressing, and on the suppression of the surface states with the magnetic field and increasing temperature, the weak anti-localizations graph like behaving like this, the gap is continuously increasing here. And with the weak localization at the different temperatures, with the increasing temperatures also they are showing the gap is increasing continuously. Important thing, the second is the SDH oscillations. And third one is the conductance quantization in the quantum transport of the topological insulators. We are discussing here what is the quantum oscillations, in what type of materials these quantum oscillations occurs, and this is the animation have been shown here, the continuous the quantum oscillations. We are discussing further this graph in the upcoming slides, and how the formation of the Landau level, density of states, vary phase, and what they are the important of the quantum conductance and the quantum oscillations. And these are the some important notes here to for the quantum oscillations. They reveal the information about the Fermi surfaces, electron effective masses, and scattering mechanism. These are very helpful to identify topological materials while and dark fermions. They are used to probe high temperature superconductors and low diagonal systems. So the quantum oscillations, what are the quantum oscillations? These are the fluctuations in the magnetoconductive resistivity at low temperatures and high magnetic field, and refer to periodic variations in the material's electronic properties, means to say that across the density of states they showing some fluctuations kind of the behavior, and due to which the quantum oscillations are occur. In what type of materials quantum oscillations came? These are mostly observed in the narrow bandgap semi-materials like topological materials, semi-metals, dark materials. How the Landau levels and quantization. The formation of the Landau levels because of these materials are very narrow bandgap materials, and across the Fermi energy they cross the density of states, and with the density of state that and at a particular level they are the energy levels, and with these energy levels up to a certain value of the Landau levels, these energy levels are the degenerate levels. Electron can go in the different levels, and means to say that the because the energy of these levels are same, so electron can oscillate, and with the increment of the magnetic field the strength are increasing, the Landau levels are degeneracy increasing with the magnetic field, and this showing the quantum oscillations. And these are some two important lines for the quantization. The quantization of charged particles cyclotron orbits in homogeneous magnetic field. As a result, the charged particles can occupy orbits with discrete equidense energy values, which are referred to as Landau levels. We are discussing here, and this is the Berry phase, the term of the mathematical which are very important. This is the geometric phase calculation, means to say like that in the Gauss-Bonnet form, this the calculation of the surface area, but this in the case of the billion zone, this is the calculation of the periodic potentials. Periodic potentials in because in the topological insulators, this is the billion zone surface area calculations, and this states the crustal momentum and Berry curvature, and with this Berry curvature this gives the Chern number, and this is similar like to as the genus, and in the physics this is distinguished by the Chern number. And this is the important of the quantum oscillations, the discussion here. This is the sphere with by externally, if we stress this sphere, and if we stress this sphere and again continuously applying pressure more and more, this sphere change into this ellipse, but this ellipse has the surface area is equivalent to this sphere, and there is the genus between to both of them, this is equal to 0, and the deformation of the continuous sphere and ellipse are same because they have the same surface area and genus. But if we applying more and more pressure, this change into donut, and means to say that if we remove this external pressure from here, this will not go back to this sphere and this ellipse, but in these both of them, these can go from, if we remove from the pressure from the ellipse, it can go back to sphere, and they are two both in the deformation process, and they are in the continuous deformation process, and they two are in the both topological state, but this is break the topology. And similar to in the quantum materials, if we applying the magnetic field, uh, similar to the like similar to like the similar to like the pressure here. So if we applying the magnetic field here, the more density of states close to the Fermi energy, and if we remove the magnetic field, the electron can go back from to the certain these states, and means to say that this is the continuous deformation. But after a certain value of the magnetic field, if we continuously increase the magnetic field, and the density of states not close to the Fermi energy, and with this that the topology is break. And this is similar to of this uh, graph, means to say that this is to the means to say that this is the conventional behavior like to the football and the sphere, and this is the quantum mechanical behavior of the particles, and this is the real space picture of like to football to the sphere, and this is the Fourier space picture. And the quantum oscillations have been shown here are going to with the increment of the magnetic field, and with the increment of the magnetic field the Landau levels quantization increases, and the cyclotron orbit's radius is converging towards to the neutrality, means to say that the more Landau levels creation are increasing, and with the increment of the magnetic field the oscillations are increasing. But these are showing here with the magnetic field here is not equal to 0, means to say that here is the magnetic field, with the magnetic field increasing the energy states crosses to the Fermi energy, and this gives the Landau levels, and with the corresponding one Landau levels there are energy states, and these energy states are in the same, and these are the degenerate states. With this that the electron can oscillate in the different levels and give the periodic oscillations. According to this cross the Fermi energy here, and after applying a very high magnetic field, electron cannot cross the density of state cross not to the Fermi energy, and due to which the oscillation suppresses on after a very high value of the magnetic field. The continuous oscillations are showing here. These are the energy states. These are the quantized energy in states with the particular Landau levels. These energy states are same, and electron can either go from these states to these states. Electron can decides in these states, but electron can, because these are a particular value of the Landau level, electron can go from here to there, and this showing the quantum oscillations, and in the resistivity, longitudinal resistivity, and this is the magnetoresistivity, and this again showing here with the increment of the magnetic field this passes to the Fermi energy, and with this showing the quantum oscillations with the magnetic field, and at a particular value of the high magnetic field this suppresses because electron cannot further go to the cross to the Fermi energy. So this suppresses the quantum oscillations, very high value of the magnetic field, so breaks. Thank you. And this is again also the in the topological, the earth revolve around the sun, and this is continuously space time distortion here, and with this is also in the topological nature.